Find the volume that would be created by revolving the cross-sectional area shown around the x-axis. So one of the first things I like to do is try to sketch the shape in 3 dimensions if I can, in order to understand what it is we're talking about here. So I'll take that cross section and we want to spin it around the x-axis, creating circles with the height of the graph. And what it makes is basically a cylinder. And we want to use what is called the disk or washer method to integrate and find the volume of this cylinder. Now for a shape like this, there is a geometry formula we can use to find it, but we want to be able to do it through calculus first and just make sure our approach matches up with that geometry formula. So that's what we'll do. To use the disk or washer method, you want to slice the shape into wheels or plate-shaped objects. And so we want thin slices. And I want to draw a typical slice so that I can label it with some different dimensions that may be useful. Okay, there's my typical disc. And I'd also like to project it back onto the original cross section just to see what the shape would look like here. There would be a rectangle, and that would match up with this line right here. I'm going to call it R for radius. And notice that that height here would also match the height of the cross section on the 2-dimensional graph too. And that's typically what we want to start with, is we want to start with one line in our cross section that we can give a formula to. So what's our function here? Well, the top of our cross section has the function f of x equals 4. That means the radius of every slice in my shape is going to be 4. So it's an easy one to start with. Next, we want to know what is going to be the width of our disk. Well, we're cutting it up along the x-axis, and we want to have an infinite number of slices here that are infinitely thin. If they're infinitely thin, then we won't call the width x. We're going to call it dx, where d stands for infinitely small. Okay, are there any other important quantities that we should label with variables here? Well, how about this? the overall volume of the cylinder would be called V, big V. But the volume of an infinitely thin disk would be called dV, an infinitely small volume. Every disk would have a surface area. And how should we label that? Should it be called dA or just A? And it's a critical question to consider when it comes to labeling these things and dealing with them correctly. Anything that's infinitely small has a D in front of it. But if a certain quantity has a substantial amount of area or a substantial amount of length, then we would not put a D in front of it and just let it be the variable. So in this case, it's not dA, it's A. So we know from geometry that an area of a circle has the formula pi r squared. Okay. And we also know from geometry that the volume of a cylinder is going to be pi r squared times the height of that cylinder. So I like to write down geometry formulas that could be useful in the integration. And so we'll start with those. Now sometimes in problems to come, we'll see that the radius of our typical shape will change depending on where you're located on the x-axis. We're not going to do one that complicated just yet. We're doing a simple cylinder one where the radius doesn't change. But if it were to change, then I would call this r of x, which means that the radius could be a function of x. So depending on what input x you're at, the formula determines what radius you get. In this case, it's just a simple constant. And so it would be totally fine to leave the x off. The x is just not necessary. And you can always leave the x off if you want, but for some variables, it's implied that they are functions of x. In this case, r does not need to be a function of x. It's just constant. Now let's build it to the next higher level. Start with one dimension, which is just a line. Then you build it to 2 dimensions. I'll replace r of x with a 4. So here, every slice of the cylinder is going to have the same surface area. It's going to be 16 pi. Now we're going to take that volume formula and we're going to build from 2 dimensions up to 3 dimensions. But I don't want to put v equals here. I want to find a way to give a formula for dv. Okay, so whereas v equals pi r squared h, and delta v equals pi r squared delta h, what I want to write here is dv equals pi r squared dh. Now we have a relationship that's a differential relationship. Now we could also say that dv equals a dh. And since here our height of the thing is dx. Let's make one more substitution. dv equals a dx. That's a great way to describe the volume of that disk. And that's what I want to use here. Now we're ready to do the integration. We want to add up all the volumes of these infinitely thin slices. And the way we do that is by integrating both sides of this differential equation. Put an integral on the left and an integral on the right. And what we end up having here is the total volume, V, but it's going to be an integral of the 16 pi dx. We want a definite volume and a final number for our answer, so we do want to put limits on this integral. And our limits have to match the type of variable that's being used in the integration. So this is a dx, so we have to put x values here. We'll go from x equals 0, that's this point, to x equals 8. And what this says is just add up all the disks from 0 to 8. Okay. Take our antiderivative. Do it from 0 to 8. $128 pi. Now let's just verify that that is valid by using the geometry formula for a cylinder that we know. We said before that the volume of a cylinder would be pi r squared h. So according to our picture here, the radius is 4. And the height of the whole cylinder would have been 8. The volume is 128 pi. So it looks like we did it correctly.